Hold up your hand and look at the space just past your fingertips. It seems like nothing at all, no colour, no weight, just a gap you could wave through without feeling a thing. Now picture sealing that gap inside a jar, pumping out every last atom of air, and cooling what remains until it is colder than the deepest reach of space. You would expect to be left with pure emptiness. Instead, that emptiness is still faintly alive, carrying an energy that never switches off and that nothing you do can take away. That restless nothing has a name. Physicists call it the quantum vacuum, and it may hold far more than the word empty allows. If you like watching the invisible become clear, take a moment to subscribe, and we can keep going together. We will build this idea up slowly, one plain step at a time, starting with a simple question. When you empty a box completely, what is truly left inside? Hold a glass jar in your hand and look at the space inside it. Right now that space is full, even though it looks like nothing. It carries air, and air is a crowd. In a single breath of it, packed into that jar, there are more molecules than there are stars in every galaxy we can see. They race in all directions at the speed of a rifle bullet, striking the glass billions of times a second, and the soft, steady pressure of all those tiny hits is the only reason the jar does not crumple in your grip. What you call empty is really a swarm you cannot feel. So take the swarm away, fit the jar to a good pump and start pulling the air out. The first stroke is easy. The molecules are so eager to fill any opening that they rush toward the pump on their own. Stroke after stroke the crowd thins, the pressure drops, sound begins to fail inside because there is less and less air to carry it. A ringing bell sealed in there would grow faint and then silent, its hammer still swinging against a clapper that makes no noise because sound needs a medium and you have taken the medium away. Keep going and you reach the limits of an ordinary pump. To empty the jar further you need better tools, the kind built for laboratories, and even those leave something behind. The best vacuum chambers ever made on Earth still hold a scattering of stray molecules, a few hundred in each thimble of space where trillions upon trillions once flew. That is emptier than the space between the planets. To beat it, you would have to leave the ground entirely and drift out past the edge of the galaxy, into the deep dark between the stars, where a person could sweep a hand through a whole cubic meter and pass through only a handful of hydrogen atoms. Picture yourself out there, floating in that thinnest place, holding your open jar. Then imagine one last effort. You catch the final few atoms and coax them out through an impossibly fine valve, until not one particle of matter is left inside the glass. No air, no dust, no single wandering atom. And to be thorough, you cool the walls of the jar toward the coldest temperature the universe allows, so that even the faint warmth of the glass cannot shed light or heat into the space you have cleared. You have done everything a person could do to make a box that holds nothing. Now ask the simple question at the heart of this whole story. What is left inside? The honest answer from everyday life is nothing at all. Empty is empty. A box with the contents removed is a box with nothing in it, and there is nothing more to say. For most of human history, and for most purposes even today, that answer works perfectly well. You do not need to know what fills a vacuum to build a light bulb or a thermos or a spacecraft. But when physicists went looking carefully with instruments delicate enough to feel the faintest whisper, they found that the answer is wrong. The empty jar is not truly empty. Something remains inside it that you cannot pump out, cannot cool away, and cannot switch off. It has no atoms and no air, yet it carries energy, and that energy stirs and flickers without pause, even at the lowest cold the laws of nature permit. This restless remainder is what physicists mean when they say the word vacuum. Not a blank, but a background. Not stillness, but a hum. To understand how anyone came to believe such a strange thing, we have to go back to a time when the vacuum was not a hum at all. It was a fear, a thing that could not exist, a hole in the world that nature itself was thought to hate. For most of 2,000 years, learned people held a single firm belief about empty space. They believed it was impossible. The idea traces back to the Greek philosopher Aristotle, who taught that a true void could not exist anywhere in the world. If you removed everything from a region, he reasoned, the surrounding matter would rush in to fill the gap before the gap could ever open. Nature, in his view, would not tolerate a pocket of pure nothing. Later thinkers gave this idea a name that stuck for centuries. They called it horror vacui, the fear of the void, as though the world itself recoiled from emptiness. That belief was not foolish. It matched what people saw. Suck on a straw and water climbs to follow your breath, as if it will not allow a gap to form. Pull a plunger and the fluid chases it. Everywhere they looked, matter seemed to leap in to close any opening, and so the conclusion felt like plain common sense. The trouble was that common sense had mistaken the cause. The water was not fleeing a void out of dread. It was being pushed from behind and below by the weight of the air pressing down on everything. The person who cracked this open was an Italian named Evangelista Torricelli, a student of Galileo. In the 1643, he took a long glass tube, sealed at one end, and filled it with mercury, a metal so dense that a small column of it weighs a great deal. He covered the open end, turned the tube upside down, and stood it in a dish of more mercury. The mercury inside did not all pour out. It sank a little, and then stopped, leaving a column standing about 30 inches tall, held up by nothing he could see. Above that column, in the sealed top of the tube, was a gap, and that gap was the thing everyone had said could not exist. No air had gotten in, no mercury filled it. It was a genuine emptiness, made on purpose, sitting quietly at the top of a glass tube on a table. We still call that pocket a Torricellian vacuum in his honour, and it was among the first true vacuums a human being ever deliberately produced. Torricelli understood what held the mercury up. The air outside had weight, and it pressed on the exposed mercury in the dish, and that pressure supported the column exactly as high as its own force allowed. He had built the first barometer without quite meaning to, and he said as much, describing all of us as living at the bottom of an ocean of air. The French thinker Blaise Pascal pressed the point further, arranging for the same apparatus to be carried up a mountain where the air is thinner. Higher up, the mercury column fell, just as the weight of air idea predicted. The fear of the void was giving way to the physics of pressure. Then came a demonstration no one could ignore. In the German town of Magdeburg, a man named Otto von Guericke built two large copper hemispheres that fit together into a sphere, and he pumped the air out from inside. With the void within holding them shut and the full weight of the atmosphere pressing them together from outside, teams of horses harnessed to each half strained and heaved and could not pull the sphere apart. The empty space inside had, in a sense, won. The void was real. It could be made and held and even put on a stage. What no one yet suspected was that this hard-won emptiness would turn out to be far stranger than any fullness. Once the vacuum was real, a new puzzle grew inside it, and this one was about light. Sound had already taught an early lesson. Ring a bell in an empty jar and the sound dies, because sound is a wave that needs a substance to travel through, and in a vacuum there is nothing to carry it. So the natural expectation was that light should behave the same way. Light is also a wave, and every wave anyone had ever studied travelled through some medium, water waves through water, sound waves through air. A wave was a disturbance, and a disturbance needs something to disturb. Yet light crosses the vacuum easily. It streams from the sun across 93 million miles of near-perfect emptiness, through the void between the planets, and reaches your eye without any air along the way. If light is a wave, and a wave needs a medium, then the space between the sun and the earth could not be truly empty after all. Something had to be there to wave, so physicists proposed that something. They called it the luminiferous ether, the light-bearing medium, and they imagined it as an invisible substance filling all of space, even the parts swept clean of air. Light was supposed to be a ripple in this ether, the way sound is a ripple in air. The ether had to be strange. It had to be thin enough for planets to glide through without slowing, yet stiff enough to carry light at its enormous speed. Nobody had ever touched it or weighed it, but the logic seemed airtight. If light waves, there must be an ether. The way to test it was clever. The Earth moves through space as it orbits the Sun, so if it were ploughing through a sea of ether, there should be an ether wind blowing past us, like the breeze you feel from a moving car. Light travelling with that wind should run a little faster than light travelling across it. In 1887, two Americans, Albert Michelson and Edward Morley, built an instrument sensitive enough to catch that tiny difference. They split a beam of light, sent the halves along paths at right angles to each other, and recombined them to compare their timing with exquisite care. They found nothing. No matter which way they turned the apparatus, no matter the season, the light took exactly the same time along both paths. There was no ether wind. The result was so clean and so unexpected that it unsettled physics for a generation. The medium that light supposedly needed left no trace at all. The resolution came in 1905 from a young clerk in a Swiss patent office named Albert Einstein. In his theory of special relativity, he simply let the ether go. Light, he proposed, does not need a medium at all. It travels at the same fixed speed for everyone, and that speed is woven into the structure of space and time themselves. There is no invisible sea to ripple. The wave carries itself. With that, the ether vanished from physics, and space was left as a bare stage. Light could cross it, but nothing physical filled it. For a while, the vacuum looked truly and finally empty, a clean nothing across which light simply flew. That picture felt like a hard-won victory, a scrubbing away of an imaginary substance. But it did not last long. Even as the ether died, another idea was quietly growing, one that would put a kind of substance back into empty space, though of a subtler and more real kind than any ether. That idea was the field. The field began not in empty space, but in a laboratory full of wire and iron. In the early 1800s, an Englishman named Michael Faraday was studying magnets and electric currents. Faraday had almost no formal mathematics. He had left school young and come up through a bookbinder's shop, and he thought in pictures rather than equations. When he laid a magnet under a sheet of paper and scattered iron filings on top, he saw the filings arrange themselves into graceful curved lines, arcing from one end of the magnet to the other. Most people saw a pretty pattern. Faraday saw something real. He became convinced that those lines were not just a trick of the filings. He believed the space around the magnet was genuinely changed, filled with something that reached out and gripped iron and other magnets even across a gap. He called these reaching influences lines of force, and he imagined them threading all the space around every magnet and every charge. To Faraday, the space around a magnet was not empty. It was in a state. It held a condition, an invisible tension, ready to push or pull anything sensitive that entered it. This was a radical thought. The accepted view was that magnets and charges tugged on each other directly across empty distance, reaching out and touching with no go-between. Faraday's picture was the opposite. Nothing acted across a gap directly. Instead, the magnet altered the space next to it, and that altered space affected the next patch over and so on, the influence passing along from place to place. The empty region carried the force. The stage was doing something. Faraday could see it but could not fully write it down. That task fell to a Scottish physicist named James Clerk Maxwell, who took Faraday's pictures and gave them the exact language of mathematics. In the 1860s, Maxwell wrote a set of equations describing how electric and magnetic fields behave, how a changing electric field creates a magnetic one, and how a changing magnetic field creates an electric one. The two fields fed each other, and when Maxwell followed his own equations to see how such linked disturbances would travel, he found they would move as a wave at one particular speed set by the properties of empty space itself. That speed came out to about 186,000 miles every second. It was the measured speed of a light, and the match was no accident. Maxwell had discovered that light is an electromagnetic wave, a self-sustaining ripple of electric and magnetic fields marching through space. And here was the quiet surprise hiding in his equations. To set the speed of light, the vacuum had to have measurable properties of its own, two constants that describe how strongly it responds to electricity and to magnetism. Empty space had to carry these numbers built in, so the vacuum that had just lost its ether gained something more subtle. It was not filled with a substance you could bump into, but it was not a pure blank either. It was a medium for fields, a place with definite properties, able to hold electric and magnetic tension, and to pass a wave of light along at a speed those properties fixed. The field lived in the emptiness and gave it structure. For a while, the field was thought of as smooth and continuous, a gentle landscape draped over space, taking any value at all, able in principle to fade all the way to zero and lie perfectly still. That last assumption, that a field could rest at exactly nothing, felt too obvious to question. It was about to be overturned by a new physics that ruled the very small, and once it fell, the empty vacuum was gone for good. The field as Maxwell left it was smooth. You could turn it up or down by any amount, brighten a light steadily or dim it to a whisper, and there seemed no smallest step. But when physicists looked closely at how light and matter actually trade energy, that smoothness broke. Energy did not flow in a continuous stream. It came in tiny fixed lumps. A German physicist named Max Planck stumbled onto this at the turn of the 20th century while studying the glow of hot objects, and he found he could only match the data if energy came in discrete packets. Einstein soon showed the same was true of light itself, which arrives in grains we now call photons. The gentle continuous field had a grainy secret. Out of this grew quantum field theory, the deepest picture we have of what fills the world. Its central idea is both strange and beautiful. Take the electromagnetic field, the thing that carries light, and imagine it spread everywhere, filling all of space the way Maxwell described. But now this field can only hold energy in whole units. When you add 1 unit of energy to the field at a particular frequency, that unit is a photon, a particle of light. The photon is not a separate object riding on the field. It is a ripple in the field, a single quantized wave, the smallest disturbance the field is allowed to carry. Then comes the leap that reshapes everything. If the light field works this way, so does everything else. There is not only an electromagnetic field, but an electron field, spread through all of space, and an electron is a ripple in it. There is a field for each kind of quark, a field for the muon, a field for the neutrino, a whole set of them overlapping everywhere at once. Every particle you've ever heard of is a stirring in one of these fields. 2 electrons are identical because they are 2 ripples on the same underlying sea, and a wave here is no different from a wave there. This picture answers an old riddle without fanfare. It explains why every electron in the universe is exactly the same, down to the last decimal, sharing the same mass and the same charge with no variation at all. They are the same because they are not really separate things. They are matching disturbances of one field, the way every ripple on a pond has the same character because it is the same water rising and falling. Create a particle, and you have plucked the field into motion. Destroy it, and the field goes quiet again in that spot. The particles come and go, but the fields are always there, and now the fields are everywhere, underlying every point of space, including the space inside your emptied jar. This changes the meaning of empty in a way that is easy to miss but impossible to undo. When you pumped out the air and swept away every atom, you removed the ripples. You quieted the electron field and the photon field and all the rest to their lowest state. But you did not remove the fields themselves. You cannot. They are woven into space. What you called an empty box is a box still filled, edge to edge, with fields lying as quiet as they are allowed to be. So the real question sharpens. If the vacuum is these fields at rest, How quiet can they truly be? Can a field be perfectly still, held at exactly zero everywhere, flat and motionless and carrying no energy at all? That is the state everyone assumed the vacuum was in. It is the smooth pond with not a single wave, and it is precisely here that the quantum world says no, for a reason that turns out to sit at the very heart of nature, in a rule about how well anything can ever be pinned down. The reason a field cannot lie perfectly still comes from a discovery made in 1927 by a young German physicist named Werner Heisenberg. He was working through the strange new mathematics of the quantum world, and he found a limit built into nature that no instrument and no cleverness could ever get around. It is called the uncertainty principle, and it says something plain once you strip away the equations. There are pairs of things about any object that you cannot both know exactly at the same time. Pin one down precisely, and the other blurs. The most famous pair is position and motion. If you know exactly where a particle is, then how fast it is moving becomes completely uncertain, and the sharper you fix its place, the wilder its speed becomes. And if you know exactly how it is moving, then where it is spreads out into a haze. This is not a matter of clumsy measurement or imperfect tools. It is a feature of the thing itself. A particle simply does not possess a perfectly definite position and a perfectly definite motion at the same instant. Nature does not allow that much certainty to exist at once. You can feel why this matters by imagining you tried to make a particle hold perfectly still. To hold still means two things together. It means sitting at one exact spot, and it means having exactly zero motion, not drifting at all. But those are precisely the two things you're forbidden to have at once. Perfect stillness would mean perfect knowledge of both position and motion, and the uncertainty principle rules that out. A quantum particle can never be fully at rest. There is always a residue of jitter it cannot shed, because shedding it would violate the deepest bookkeeping of the world. Now carry that same rule to a field. A field, at each point in space, has a value, which is like its position, a number saying how strong it is right there. And it has a rate of change, how fast that value is shifting, which plays the role of its motion. The uncertainty principle binds these two together exactly as it binds a particle's place and speed. You cannot have the field sitting at a precise value and also perfectly unchanging at the same time. If the field held at exactly zero everywhere and stayed flat and motionless, you would know both its value and its rate of change with perfect precision. That is forbidden. So the field can never be truly flat, even in its lowest, quietest state. Even with every particle removed and every ripple stilled, it must keep trembling a little. The value at each point wavers around zero, never settling, dipping high and low in a restless quiver that cannot be calmed. Push the trembling down in one way and it springs up in another, because the rule always demands its due. The vacuum is not a still pond. It is a pond that shivers on its own, with no wind forever, because the law of the world will not let it hold still. This trembling has a name. Physicists call it vacuum fluctuation, the ceaseless quiver of every field even in perfect emptiness. It is small, far too small to feel or to see with the eye, but it is real, and it never stops, and nothing you can do will make it stop. Cool the vacuum toward the lowest cold there is, and the quiver remains, because it does not come from heat. It comes from the uncertainty woven into the fields themselves, and that quiver carries energy, a faint restless energy present in truly empty space, which is the next thread to pull, because that energy has a name and a story of its own. The energy of the vacuum's quiver has a name that describes exactly what it is. Physicists call it zero-point energy, the energy that remains at the 0 point, the lowest state, when everything that can be taken away has been taken away. It is the energy a field keeps even when it holds as little energy as the laws of nature permit. You cannot spend it or drain it, because there is nothing lower to fall to. It is the floor of the world, and the floor is not at zero. The story of this idea has a quiet beginning that is often skipped over. Max Planck, the same man who first found that energy comes in packets, returned to his work a few years later around 1912 and built a second version of his theory. In this refined picture, he noticed that his equations came out cleaner if each little oscillator of the field kept a small leftover of energy even at the lowest temperature, a piece that never went away. It was half of one energy packet, half of a single quantum, held in reserve no matter how cold things became. Planck had written down the first hint of zero-point energy, almost in passing, as a term that simply refused to vanish. To picture what that half-quantum means, think of a field as built from countless tiny modes, each one able to vibrate at its own frequency, like the strings of an enormous instrument tuned across every possible pitch. A single string, in the everyday world, can be plucked to ring or left silent and perfectly still. But a quantum string cannot be perfectly still, for the reason the uncertainty principle already showed. Even when it holds the least energy it can, it keeps vibrating faintly, and the energy of that faint, unavoidable vibration is exactly half a quantum, half of the smallest ordinary lump of energy that string could carry. Now sum it up. The field is not one string, but an unimaginable number of them, one for every frequency and every direction and every point you could name. Each keeps its half quantum, its small unspendable share, and together they fill space with a background of energy that is present everywhere, in every cubic inch of the emptiest vacuum. This is the hum promised at the very start. It is not the warmth of leftover heat, which cooling could remove. It is the sound of the fields themselves, unable to fall silent, singing their lowest note forever. There is a puzzle hiding in that sum, and honesty requires naming it now, even though its full weight comes much later. If you add up the half quantum from every possible mode, and you let the frequencies climb without limit, the total energy does not settle to a sensible number. It races off toward infinity. Taken at face value, the math says empty space should hold an endless supply of energy in every tiny volume, which is plainly not what we see. Something is wrong with the naive count, and physicists have spent decades wrestling with how to tame it. For now, hold the tension lightly. The vacuum's energy is real, its exact amount is deeply unsettled, and both of those things are true at once. What is not in doubt is the basic fact. The lowest state of a quantum field is not a state of no energy. It is a state of least energy, and least is not none. Every mode keeps its half quantum. Every field trembles at its floor. The emptiness carries a cost that cannot be refunded. To make this concrete, and to see that it is not just a bookkeeping trick, it helps to look at the simplest system in all of physics where this flaw appears, a single humble oscillator that will not hold still even at the coldest cold the universe allows. The simplest place to see zero-point energy is a system so plain it appears in every physics course. It is called the harmonic oscillator, and it is just anything that swings back and forth around a resting point, pulled back whenever it strays. A weight bobbing on a spring is a harmonic oscillator. So is a pendulum swinging gently, and so is an atom jiggling in place inside a solid. Whenever a thing is nudged from its rest and pushed back toward it, in proportion to how far it has gone, it swings in this same steady way, and the mathematics that describes it is the same across all of them. In the everyday world, such an oscillator can be brought to a complete stop. Let the spring wind down, let friction drink away the motion, and the weight will hang there, perfectly still, holding no energy of motion at all. Its lowest state is dead rest. That is what our intuition insists on, and for a spring on a bench it is close enough to true. But shrink the oscillator down to the scale of a single atom, where the quantum rules take over, and the picture changes in a way that will not go away. A quantum harmonic oscillator cannot come to a complete stop. Its lowest possible state, the one it falls into when you have drained away everything you can, still holds energy. That leftover is exactly half of one quantum, half of h times the frequency, using the small number Planck first measured to set the size of quantum lumps. The oscillator keeps a faint unstoppable jiggle, a zero-point motion, and the energy of that jiggle is the zero-point energy in its purest and simplest form. There is no colder, quieter state to reach. This gentle tremble is the bottom. You can see why from the uncertainty principle without any equation. To hold perfectly still, the atom would need to sit at exactly its resting point and have exactly zero speed, both at once. But that is the forbidden pair. If it sat exactly at rest position with exactly zero motion, you would know its place and its speed together with perfect precision, and nature does not permit that. So the atom compromises. It hovers near the resting point, always shifting a little, always drifting a little, keeping just enough blur in both to satisfy the rule. That compromises the zero-point motion, and it costs a small permanent share of energy. This is not a story with no consequences. It shows up in the real behavior of matter at the coldest temperatures. Consider helium, the lightest of the noble gases. Cool almost any substance far enough and it freezes solid, its atoms locking into a rigid grid. But helium, at ordinary pressure, refuses to freeze no matter how cold you make it, all the way down toward the lowest temperature there is, about minus 460 degrees on the Fahrenheit scale. It stays a liquid. The reason is zero-point motion. Helium atoms are so light and so weakly held that their unavoidable quantum jiggle is strong enough to keep shaking the solid apart. The atoms will not sit still long enough to freeze, because the laws of the quantum world forbid them from sitting still at all. So the coldest cold is not silence. It is a faint permanent hum, present in every oscillator, every atom, every mode of every field. The vacuum in the end is the ultimate oscillator, countless modes all holding their lowest note, none of them ever falling to true stillness. This much was a strange and beautiful result. But the real vacuum turned out to be stranger still, because when one physicist tried to make quantum theory agree with Einstein's relativity, he was forced to conclude that empty space was not merely humming. It was full. The physicist who filled the vacuum was a quiet Englishman named Paul Dirac, one of the strangest and most precise minds of the 20th century. He spoke rarely, chose each word with painful care, and trusted the beauty of mathematics almost more than he trusted experiment. In 1928, Dirac set himself a hard problem. Quantum theory described the small, and Einstein's relativity described the fast, but no one had an equation for the electron that honoured both at once, that worked for a particle both tiny and moving near the speed of light. Dirac wanted that equation, and after a long search, he found it. The equation was a triumph. It described the electron beautifully, and it even predicted on its own that the electron should spin and act like a tiny magnet, a property that had been measured but never explained. It was the kind of result that makes a physicist trust an equation deeply. But the same equation carried a passenger no one wanted. When Dirac solved it fully, it gave not one family of answers but two. One family described electrons with ordinary positive energy, exactly as expected. The other described states with negative energy, electrons that would carry less than nothing. Negative energy was a disaster on its face. In quantum theory, things tend to fall toward the lowest energy they can reach, the way a ball rolls downhill. If states of negative energy existed and were empty, every electron in the universe should tumble down into them, cascading toward lower and lower energy without end, and all ordinary matter would collapse in a flash of released light. Since matter plainly does not collapse, something had to stop that fall. Dirac could not simply throw the negative states away, because his equation insisted they were there. His solution was audacious, and it changed what the vacuum meant. Dirac proposed that the negative energy states were not empty at all. They were already full. Every single one of them, throughout all of space, was occupied by an electron. This infinite ocean of filled negative energy states he pictured as the true vacuum, the real state of empty space. Ordinary electrons could not fall into it because there was no room, a rule from quantum theory that forbids two electrons from sharing the same state. The sea was full to the brim, and its fullness is what held the world up. This meant that what everyone had called empty space was, in Dirac's picture, a sea packed with an infinite number of electrons, all in negative energy states, so uniformly present that they were undetectable. You cannot see a sea if you are a fish born inside it, and it is everywhere at once. You would notice only disturbances, only the places where the sea departed from its smooth fullness. The vacuum, the emptiest emptiness, was in this view the most crowded thing imaginable, an endless still ocean of hidden particles filling every point of space. Physicists were uneasy with the Dirac sea. It felt like a strange amount of hidden furniture to hang the world on, and the infinities in it troubled everyone, including Dirac. Later theories would recast the idea in cleaner language, without literally filling space with countless electrons. Yet the core insight survived every reworking, and it was this: the vacuum has structure. It is a physical state with rules, a thing that can be disturbed and that pushes back. And Dirac's sea made one prediction so bold, so testable, that when it came true it turned a bookkeeping trick into one of the great discoveries of the century. If the sea were ever disturbed, something new should fall out of it. The prediction that fell out of Dirac's sea was a new kind of matter, and it came from asking a simple question about the sea itself. If the vacuum is an ocean of filled negative energy states, what happens if you reach in and pull one electron up out of it, giving it enough energy to become an ordinary positive energy particle? You would now have two things. You would have a free electron where before there was only sea, and you would have a gap, an empty spot in the ocean, a place where one electron is missing from a fullness that was perfectly smooth before. Dirac worked out how that gap would behave, and the answer was startling. A missing negative charge in a uniform sea would act to any observer like a present positive charge. The whole would move, respond to forces, and carry energy, all exactly like a real particle, but with the opposite electric charge to the electron. Where the electron is negative, this whole would be positive. Where the electron has its particular mass, the whole would have the very same mass. It was, in every respect, a mirror image twin of the electron, identical in weight, opposite in charge. At first Dirac was cautious, even reluctant. He wondered if the whole might somehow be the proton, the only positive particle then known. But the proton is nearly 2,000 times heavier than the electron, and the mathematics was firm. The whole had to have the electron's exact mass. So in 1931, Dirac took the bold step and predicted a genuinely new particle, one no one had ever seen, a positive twin of the electron born from the structure of the vacuum itself. Today we call it the positron, the first piece of what we now call antimatter. The confirmation came fast and from the sky. A young American physicist named Carl Anderson was studying cosmic rays, the shower of high-energy particles that rains down on the Earth from space. He used a cloud chamber, a device that makes the paths of charged particles visible as thin trails of mist, and he placed it in a magnetic field which bends the path of a moving charge. The direction of the bend tells you the sign of the charge, and the tightness of the curve tells you something about its mass. In 1932, Anderson saw a track that curved the wrong way for an electron, but had exactly an electron's lightness. It was a positive particle as light as an electron. It was the positron, exactly as Dirac had foretold. Here was one of the most remarkable moments in the history of physics. A man had stared at an equation, been troubled by an unwanted mathematical passenger, refused to throw it away, and instead followed it to the claim that a brand new form of matter must exist. And then the sky delivered it, right on time, matching the prediction in every detail. The vacuum had, in a real sense, given birth. Something had come out of the emptiness that no one had known was there, and it had been hiding in the mathematics of empty space all along. Antimatter turned out to be a general rule, not a quirk of the electron. Every particle has an antiparticle, a twin with opposite charge, and when a particle meets its antiparticle they annihilate, vanishing in a burst of energy, usually as light. This is the deepest reason the vacuum can never be simply nothing. Given enough energy, empty space can produce a particle and its antiparticle together out of what looked like pure emptiness, so long as the books balance. That hint that the vacuum can lend out particles if only for an instant leads straight to one of the strangest and most useful ideas in all of physics: the flickering ghosts that fill the modern vacuum. The flickering ghosts of the modern vacuum are called virtual particles, and to understand them you have to return to Heisenberg's uncertainty principle and notice a second face of it. The version we met earlier linked position and motion, but there is another pairing just as fundamental that links energy and time. It says that over a very short interval, the energy of a system is not perfectly fixed. The briefer the moment you consider, the more the energy is allowed to blur. For a long stretch of time, energy is pinned down tightly and must be conserved with great care. For a fleeting instant, it can wander. This opens a loophole in one of the strictest rules in physics. Normally, you cannot make something from nothing, because that would create energy out of empty space, and energy is conserved. But over an extremely short time, the energy books are allowed to go briefly out of balance, as long as they are settled again before anyone could ever check. So the vacuum can borrow energy, use it to bring particles into being for the tiniest sliver of a moment, and then pay it all back by letting those particles vanish. The shorter the loan, the more it can borrow. The universe permits the debt only because it is repaid before the deadline. What appears in these brief flickers are particle and antiparticle pairs, born together and gone together. Out of the empty field, an electron and a positron may wink into existence, drift an unimaginably small distance apart, and then find each other and annihilate, all in a span of time far too short to ever catch them directly. The same happens with pairs of every kind, quarks and antiquarks, and even fleeting photons. These are the virtual particles. The word virtual does not mean imaginary. It means they exist on borrowed time, never as free particles you can capture, only as brief internal flickers of the vacuum itself. So the picture of empty space transforms once more. It is not the still hum of fields alone. It is a seething, boiling froth, a constant flicker of pairs appearing and vanishing everywhere, at every instant faster than any clock can follow. Physicists sometimes call this the quantum foam. Every tiny volume of the emptiest vacuum is alive with these momentary comings and goings, a restless churn of ghostly matter that borrows its existence from the uncertainty of the world and gives it back before the bill comes due. The jar you emptied is quietly boiling. It would be fair to be skeptical here. This sounds like the kind of story physicists might tell themselves, a colourful picture with no way to check it. If virtual particles can never be caught, if they always vanish before any instrument could touch them, then how could anyone know they are real, and not just a convenient fiction in the equations? That is the right question to ask, and it has a firm answer. The virtual particles cannot be caught, but they leave marks. They reach out and touch the real particles around them, nudging their behaviour in ways that can be measured with staggering precision. Those measurements are where this whole story stops being a tale and becomes hard science. To make sense of them, and to control the infinities that the virtual particles kept throwing into the mathematics, physicists had to build one of the most successful theories ever devised. A theory of how light and electrons and the restless vacuum all fit together. 3 people built it, working separately, and their creation would predict the effects of empty space to more decimal places than any other theory in history. The theory that tamed the vacuum's flickers is called quantum electrodynamics, usually shortened to QED, and it describes how light and matter interact when both obey the quantum rules and the rules of relativity. It grew up in the years right after the Second World War, and it grew up in trouble. Whenever physicists tried to calculate anything precisely, the virtual particles of the vacuum kept spoiling the answer. Their sums ran off to infinity, just as the 0-point energy had. A calculation that should give a clean number gave an endless one, and for a while it seemed the whole approach might be broken beyond repair. 3 physicists solved it, working on separate continents and largely out of contact. In the United States, Richard Feynman invented a new way of picturing the whole business, drawing simple diagrams of lines and vertices that stood for particles meeting and parting, virtual ones included. Each diagram was a term in a calculation, and the pictures made a fearsome mathematics almost visual. Also in the United States, Julian Schwinger built a more formal and rigorous version, dense with careful algebra, that reached the same results by a stricter road. And in Japan, working in near isolation in the aftermath of the war, Shinichiro Tominaga had arrived at much the same ideas independently, a little earlier, unknown to the others. Their shared breakthrough was a procedure called renormalization, and it was as clever as it was uncomfortable. The infinities, they realized, always attach themselves to a few quantities, like the electron's mass and its charge. But we never see the bare electron alone. We only ever see an electron already wrapped in its cloud of virtual particles, already dressed by the vacuum around it. So the values we measure in the laboratory are the dressed values, the ones that include all those vacuum effects. Renormalization was the disciplined art of folding the infinities into those measured quantities, absorbing the endless parts into the numbers we get from experiment, and leaving behind finite, sensible answers for everything else. Many physicists, Dirac and Feynman among them, remained uneasy about renormalization, feeling it was more a trick than a true understanding. Feynman himself called it a shell game and a way of sweeping infinities under the rug, and yet it worked, with a precision that silenced most doubt. Once the procedure was in place, quantum electrodynamics could calculate the effects of the seething vacuum on real particles and get numbers, definite numbers, that could be checked against careful measurement. For their work, Feynman, Schwinger and Tominaga shared the Nobel Prize in 1965. What made the theory more than a mathematical patch was exactly this ability to predict. If the vacuum truly boils with virtual particles, and if those particles truly reach out and touch ordinary matter, then their touch should shift the behavior of real electrons and real atoms by tiny, specific, calculable amounts. QED turned the poetry of the quantum foam into a set of firm predictions. It said, in effect, here is precisely how much the restless vacuum should nudge this atom, down to many decimal places. And that turned the whole question into something an experimenter could settle. The stage was set for a confrontation between theory and measurement of a kind physics had rarely seen. The vacuum was supposed to leave fingerprints on the most ordinary things, on the light from a simple hydrogen atom, on the magnetism of a single electron. If those fingerprints were there, and if they matched the numbers, then the boiling emptiness was no story. The first of these fingerprints to be found came from the simplest atom there is, and it was so subtle that finding it at all was a triumph of patience. The first clear fingerprint of the vacuum was found in the light of hydrogen, the simplest atom in the universe, a single electron bound to a single proton. By the 1940s, physicists thought they understood hydrogen thoroughly. Dirac's equation described its electron with great success, and it predicted the energies of the electron's various states, the rungs of the ladder it can occupy around the proton. In particular, the equation said that two specific states of the hydrogen electron should have exactly the same energy. They should sit at precisely the same height on the ladder, indistinguishable in energy, perfectly matched. In 1947, an American physicist named Willis Lamb, working with a student named Robert Rutherford, decided to test that prediction with new tools developed during the war, tools built for radar that could probe atoms with microwaves of exquisitely tuned frequency. Lamb aimed these microwaves at hydrogen atoms and measured the two supposedly equal states with far more precision than anyone before him. And he found that they were not equal after all. One of them sat a tiny bit higher than the other, shifted by a small but unmistakable amount. Dirac's clean prediction was slightly, definitely wrong. The gap was minuscule, but it was real, and it demanded an explanation. The answer was the vacuum. The electron in a hydrogen atom does not move through empty nothing. It moves through the seething sea of virtual particles, the quantum foam and that foam nudges it. As the electron sits in its orbit, virtual photons flicker into being around it and are reabsorbed, and each little flicker jostles the electron slightly, making it quiver and smear out its position by a tiny amount. That smearing changes how tightly the electron feels the proton's pull, and it changes one of the two states more than the other, lifting it just a hair higher. This tiny difference is now called the Lamb shift, and it was the first direct measured proof that the restless vacuum touches ordinary matter. The hydrogen atom was feeling the foam. Its electron was being buffeted, ever so gently, by the borrowed particles winking in and out of the emptiness around it, and the buffeting showed up as a real shift in the colour of light the atom could emit. Something that seemed like pure philosophy, the idea that empty space is not empty, had left a mark you could read off an instrument. The Lamb shift landed at exactly the right moment. It was announced at a famous meeting on Shelter Island in 1947, and it lit a fire under the theorists who were struggling to make quantum electrodynamics give finite answers. Here was a real number, a definite measured shift that the new theory had to explain. Hans Bethe, riding home on a train from that meeting, did a rough calculation on the spot and got close to the measured value, showing that the vacuum's effect could indeed be computed. The race was on to do it properly, and within a few years the full theory reproduced the Lamb shift with growing accuracy. So the vacuum had been caught in the act, faintly, in the light of the simplest atom. But hydrogen, for all its simplicity, is still an atom with a proton and an electron and all the complications of their binding. There was a cleaner test waiting, one that involved a single particle alone, stripped of every complication, where the vacuum's touch could be measured against theory, with a sharpness that would become the most precise agreement between prediction and experiment in the whole of science. The cleanest test of the vacuum uses a single electron and its magnetism. An electron behaves like a tiny magnet, and the strength of that magnet is captured by a number physicists call its G factor. Dirac's equation, that same triumphant equation, made a clean prediction for this number. It said the electron's G factor should be exactly 2, a round and simple value falling straight out of the mathematics. For a while, 2 looked right, and it was another feather in Dirac's cap. The electron was a magnet of exactly the predicted strength. Then more precise measurements arrived, and they showed the G factor was not exactly 2. It was a little more, larger than 2 by a small fraction of a percent. The electron was slightly more magnetic than Dirac's bare equation allowed. This small excess, the amount by which the G factor exceeds 2, became one of the most important numbers in physics. It is often written as the difference, G minus 2, and it measures precisely how much reality departs from the simple prediction. And that departure, once again, is the work of the vacuum. The electron is never truly alone. It is always surrounded by its cloud of virtual particles, the flickering foam that dresses every real particle. Virtual photons stream out and back. Virtual electron and positron pairs blink into being around it. All this activity slightly changes how the electron responds to a magnetic field, nudging its magnetism a little above the bare value of 2. The excess is the sum of all these vacuum effects, each one a tiny contribution from a different way the foam can flicker around the electron. To calculate it is to add up the influence of empty space on a single particle. Julian Schwinger, one of the builders of quantum electrodynamics, did the first piece of this calculation, and his result was so clean and important that it is carved on his gravestone. He found that the leading contribution to the excess is a simple expression involving the fine structure constant, the fundamental number that sets the strength of the electromagnetic force, divided by 2 times pi. That first term alone got most of the way to the measured excess. Later physicists computed further terms, harder and harder ones, involving more and more virtual particles in ever more tangled arrangements, pushing the theoretical prediction to more and more decimal places. The result of all this labour is the most stunning agreement between theory and experiment anywhere in science. The measured value of the electron's magnetism and the calculated value, worked out from the flickering of the vacuum, agree to better than 1 part in a trillion. It is as if you measured the distance across a continent and got it right to the width of a single human hair, and then a completely separate calculation, built from the churning of empty space, gave you the very same answer to the same absurd precision. Nothing else in physics is tested this well. Sit with what that means. The theory that produces this number is built, at its heart, on the idea that empty space boils with virtual particles that touch every electron. If that idea were wrong, the calculation would miss. Instead, it hits, over and over, to 12 digits and more. The restless vacuum is not a metaphor or a loose way of speaking. It is a precisely measured feature of the world, confirmed by the most demanding comparison physics has ever made. And the same vacuum that tweaks the electron's magnetism also does something to its charge, softening and shaping the electric force itself in a way that changes what we even mean by the strength of a charge. The vacuum does not only nudge magnetism, it reaches into the electric charge itself, and to see how, imagine a single electron sitting alone in empty space, carrying its negative charge. Around it, the vacuum is doing what it always does, flickering with virtual particle pairs. Among these are countless virtual electron and positron pairs, briefly born and briefly gone, but while they exist, they feel the real electron in their midst, and they respond to it. The virtual positrons, being positive, are drawn a little toward the central electron. The virtual electrons, being negative, are pushed a little away. This is exactly what happens in an ordinary material placed in an electric field, and physicists borrow the same word for it. They call it polarization. In a block of glass or water, the molecules shift slightly in response to a nearby charge, their positive and negative ends lining up, and this line-up partly cancels the original charge, weakening its reach. The vacuum does the same thing, but with virtual pairs instead of molecules. The cloud of flickering pairs arranges itself around the real electron, positives drawn inward, negatives pushed outward, forming a kind of screen. Physicists call this vacuum polarization, and it means empty space behaves like a medium, a substance that responds to charge. The consequence is subtle and strange. The screen of virtual pairs partly hides the electron's true charge. If you stand far away and measure the electron's charge, you're seeing it through this screening cloud, and what you measure is a little weaker than the bare charge deep inside. The virtual positrons crowding close have muffled it. But if you come closer, pushing past some of the screening cloud, you feel a stronger charge, because less of the screen lies between you and the core. The nearer you get to the electron, the more of its true, unscreened charge you feel, and the stronger the electromagnetic force between you becomes. This means the strength of the electric charge is not a single fixed number. It depends on how close you look, or equivalently, on how hard the particles are slamming together when you probe it. Physicists call this a running coupling, because the effective strength of the force runs, changing with the energy of the encounter. At the gentle energies of everyday life, we measure one value for the charge. In violent collisions inside particle accelerators, where probes drive deep past the screening cloud, the effective charge is measurably larger. The force grows stronger the closer in you go, exactly as vacuum polarization predicts. This effect too has been measured, and it matches. In the great accelerators where electrons and positrons are smashed together at enormous energies, the effective strength of the electromagnetic force is seen to be larger than its everyday value, by just the amount the screening picture requires. The vacuum is not a passive backdrop through which charges shine unchanged. It is an active medium that clothes every charge in a shifting cloud, dimming it from afar and revealing more of it up close, and the exact rule for that dimming has been confirmed in the laboratory. So the emptiness by now has become almost tangible. It hums with zero-point energy. It boils with virtual pairs. It touches the magnetism of a lone electron to 12 decimal places, and it wraps every charge in a screen that changes the very strength of the electric force. Each of these is a way the vacuum leaves its mark on particles that were already there. But there was one more prediction, bolder than all of these, that asked something new of the emptiness. It asked whether the vacuum could push on ordinary objects directly, whether two plain metal plates, with nothing between them but empty space, could be drawn together by nothing at all. The prediction that empty space could push on solid objects came from a Dutch physicist named Hendrik Casimir in 1948. Casimir was working at the Philips Research Laboratory in the Netherlands, thinking about the forces between tiny particles suspended in fluids, when he was led to a far stranger idea by a conversation with the great physicist Niels Bohr. Bohr suggested to him that his puzzle might have something to do with zero-point energy, the restless background hum of the vacuum. Casimir took the hint and followed it to a conclusion that still astonishes. Picture two flat metal plates, parallel to each other, hanging in a perfect vacuum with nothing whatsoever between them. No air, no particles, no radiation, only empty space. Common sense says they should simply hang there, feeling no force, since there is nothing between them to push or pull. But Casimir thought about the zero-point energy of the electromagnetic field in the gap, the sea of virtual photons filling all of space with their lowest hum. And he realized that the plates change that sea. They set a boundary on it. The electromagnetic field in the gap can only vibrate in certain ways between the plates, in modes that fit neatly into the space, like the notes a guitar string of a fixed length is allowed to play. Wavelengths that do not fit are excluded from the gap. But outside the plates, in the open space beyond, the field can vibrate in every mode, with no such restriction. So there are fewer modes of the vacuum humming between the plates than there are humming outside them. The zero-point energy is a little thinner in the gap than in the open, and that imbalance has a consequence. Because there are more modes pushing on the plates from outside than from the narrow space within, the vacuum presses the plates together. The push from the crowded outside beats the push from the sparse inside, and the two plates are driven toward each other by the pressure of empty space itself. This is the Casimir effect, a real force between two uncharged plates, arising from nothing but the structure of the vacuum and the way solid boundaries reshape its restless hum. The plates are squeezed together by the emptiness around them. Casimir even calculated how strong the force should be, and the answer had a strange purity. The push depends only on the size of the gap and on two fundamental constants of nature, the speed of light and Planck's constant, the number that sets the scale of all quantum effects. It does not depend on the charge of the electron or the details of the metal. It is, in that sense, a nearly pure expression of the quantum vacuum made mechanical, a force you could in principle feel, born from the counting of modes in empty space. The force is tiny, growing important only when the plates are brought extraordinarily close, closer than a hair's width, which is why no one had ever noticed it. Here was a claim as bold as Dirac's positron. It said the vacuum was not only a background that shifts atoms and dresses charges, but a thing that could reach out and move ordinary objects, pressing two plain plates together with a definite calculable force. If it were true, it would be the most direct evidence yet that empty space carries real energy and real consequence. But a calculation, however beautiful, is only a promise until someone measures it. The Casimir force was so faint that testing it would take half a century of patient work, and even once it was found, it would carry a quiet descent that most tellings of this story leave out. A calculation, however elegant, is only a promise until an experiment keeps it, and the Casimir force was so faint that keeping the promise took nearly 50 years. The first serious attempt came in 1958, when a physicist named Marcus Sparnay, working at the same Philips laboratory where Casimir had done his thinking, tried to measure the push between two flat plates. The trouble was brutal. To feel the force at all, he had to bring the plates within a fraction of a hair's width of each other and hold them perfectly parallel, and the tiniest tilt or speck of dust ruined everything. His results did not contradict Casimir, but the uncertainty was so large that he could only say the measurement was not inconsistent with the theory. That was not proof. It was a shrug. The problem of keeping two flat plates parallel at such tiny separations turned out to be nearly impossible, and it stalled the field for decades. The breakthrough came from giving up on flat plates altogether. In 1997, an American physicist named Steve Lamoreaux, then at the University of Washington, used a clever geometry instead. He replaced one flat plate with a curved surface, a sphere, set close to a plate. A sphere and a plate do not need to be aligned the way two plates do, because a sphere presents the same gentle curve no matter how it is turned. The alignment nightmare simply vanished. Lamoreaux mounted his sphere on a delicate torsion pendulum, a device that twists by a measurable amount when the smallest force acts on it. As he brought the sphere close to the plate, the vacuum's pull twisted the pendulum, and he watched the twist and read off the force. He measured the Casimir push directly, and he found it matched the prediction to within about 5%. For the first time, the force that Casimir had conjured out of the counting of modes in empty space had been felt, cleanly, in a real apparatus, at the strength the theory demanded. The measurements only got better from there. Soon after, a physicist named Umar Mohideen, working with a colleague named Anushree Roy, used an atomic force microscope, an instrument built to feel forces on single atoms, to measure the Casimir effect with far greater precision. They brought a tiny metal-coated sphere close to a plate and mapped the force across a range of separations, and the shape of the curve they traced followed Casimir's formula closely across the whole range. The agreement tightened to 1% or 2. The push of the empty gap was no longer a shrug. It was a firm, repeatable measurement. What these experiments confirmed is worth pausing on. Two ordinary objects carrying no charge, held in a vacuum with nothing between them, are drawn together. Nothing passes across the gap. No field is switched on. The only thing at work is the difference in the vacuum's hum inside the gap and outside it. The fact that fewer modes of empty space can fit between the plates than can crowd around them from beyond. That imbalance, pure geometry acting on the restless 0-point C, produces a force you can measure with a good instrument. Empty space pushes. The Casimir effect is now a settled piece of physics, real enough that engineers building the smallest machines have to account for it. In devices with parts only microns apart, the Casimir force can grab those parts and stick them together, a nuisance born of the vacuum that designers must plan around. The emptiness, once thought to be the absence of everything, turns out to be something a builder can trip over. And yet, for all this solid confirmation, there is a quieter question hiding underneath the triumph, one that the usual telling skips, and it is worth facing honestly before we go on. Does the Casimir force truly prove that empty space holds 0-point energy, or could the same push be explained another way? Here is the part most tellings leave out. The Casimir effect is often presented as direct proof that the vacuum is filled with 0-point energy, a clean demonstration that empty space really does hum with the half quantum of every mode. The story is tidy. The plates change the modes, the energy is lower in the gap, and the plates are pushed together by the restless C. But a number of careful physicists have pointed out that this tidy story may claim more than the experiment can deliver, and their dissent is a good lesson in how honest science handles its own favourite ideas. The clearest voice of this caution was a physicist named Robert Jaffe at the Massachusetts Institute of Technology. Jaffe worked through the Casimir effect with care and showed something surprising. The force between the plates can be calculated a completely different way, without ever mentioning the 0-point energy of empty space at all. In this alternative accounting, the Casimir force comes from the ordinary electromagnetic interaction between the charged particles that make up the plates, worked out through the same machinery of quantum electrodynamics that handles everything else. The vacuum's 0-point C never has to enter the calculation. The key clue Jaffe emphasized is a number that appears in the theory, the fine structure constant, the fundamental measure of how strongly charges interact. If the Casimir force were truly a pure effect of empty space, arising from the vacuum alone, its size should not depend on how strongly matter and light couple together. But when you look closely, the strength of the force does depend on that coupling. It fades away as the coupling weakens. That dependence is the fingerprint of ordinary charged matter doing the work, not of a pristine vacuum energy acting on its own. This does not mean the Casimir effect is fake, or that the measurements are wrong. The force is real, and it is measured, and it agrees with the prediction. What is in question is only the interpretation, the words we wrap around the number. One telling says the vacuum's own energy pushes the plates. Another says the plates push each other through their charged constituents, in a way that happens to give the very same answer. Both calculations land on the identical measurable force. The experiment cannot tell them apart because they agree on everything you can actually observe. So the Casimir effect, so often paraded as the smoking gun for zero-point energy, is really a subtler thing. It is fully consistent with the vacuum having zero-point energy, and that is the more common and intuitive way to describe it. But it does not force that conclusion, because a second, equally valid description reaches the same result without invoking the vacuum's hum at all. The honest statement is that the Casimir force is a genuine quantum effect involving the electromagnetic field and the boundaries placed in it, and that whether you call it a property of empty space or a property of the plates is in this case a matter of accounting. This is worth holding on to because it shows something about how the vacuum's energy sits in physics. The energy is deeply woven into the theory, and it appears everywhere in the mathematics. But pinning down a single experiment that proves it exists as a real, weighable thing is harder than the popular story admits. The vacuum's reality is not in doubt. Its behavior is measured to astonishing precision. But the plainest question, whether that background energy is a substance in its own right or a way of speaking about the interactions of ordinary matter, remains genuinely open at the edges. To find a cleaner sign that the vacuum can do something real, physicists went looking for a way to shake it hard enough that it would give up something no ordinary matter could hide, a flash of real light pulled straight out of the empty dark. If the vacuum truly seethes with virtual photons, borrowed and repaid before any instrument can catch them, then perhaps there is a way to catch one anyway. The trick would be to shake the boundary of the vacuum so violently that a virtual photon, flickering into being, does not have time to vanish before the shaking hands it enough energy to become real. Then the borrowed particle would be paid off, not by disappearing, but by turning into an ordinary photon that flies away and can be detected. You would have pulled real light out of empty space by moving a mirror. This idea is called the dynamical Casimir effect. The ordinary Casimir effect uses still plates and a fixed gap. The dynamical version demands motion, and not just any motion. To convert virtual photons into real ones, the mirror must move at a sizable fraction of the speed of light, wobbling back and forth billions of times a second. No mechanical mirror made of glass and metal can move like that. The demand seemed to place the effect forever out of reach, a beautiful prediction with no hope of a test. The vacuum would keep its light, because nothing solid could be shaken fast enough to shake it loose. The way around this came from a clever substitution. You do not actually need a physical mirror made of matter. You need a boundary that reflects the electromagnetic field, and you can make such a boundary out of something other than a slab of metal. In 2011, a team led by a physicist named Christopher Wilson, working in Sweden, built a device from a superconducting circuit, a tiny electronic loop chilled to near absolute zero, where electrical resistance vanishes. In this circuit, the effective boundary for the electromagnetic field could be shifted electronically, moved not by pushing metal, but by changing a magnetic field applied to the loop. By flipping that magnetic field back and forth at enormous speed, billions of times per second, they made the effective mirror wobble as if it were sweeping through space at a good fraction of the speed of light, far faster than any real object could travel. The vacuum inside the circuit felt this violent shaking of its boundary, and out of the empty, cold, superconducting dark came photons, real ones, in exactly the pattern the dynamical Casimir effect predicted. They had produced light from the vacuum by shaking nothing but the edge of empty space. The photons appeared in pairs, which is the signature that they came from the vacuum's virtual flickers rather than from some ordinary source of stray light. A virtual pair born together, then split apart by the shaking before it could annihilate, becomes a pair of real photons flying off in step. The team saw exactly this correlated pairing, the fingerprint of the mechanism, ruling out mundane explanations. The vacuum had been made to glow, faintly, by motion alone. This was a cleaner victory than the static Casimir effect in one respect. Here the vacuum did not merely push on plates in a way that could be redescribed as matter pushing on matter. Here the empty space gave up real, countable photons that were not there before, conjured by the violent motion of a boundary. The energy for those photons came from the machine doing the shaking, which had to work against the vacuum and pay the full cost of the light it drew out. But the light itself came from the field's own restless flickering, made real. Empty space, shaken hard enough, shines, and this same restless field, always present, always ready, turns out to be the hidden reason behind something far more ordinary and familiar: the simple fact that a glowing atom does not glow forever. Light an atom up and it will not stay lit. Give an atom energy, kick one of its electrons up to a higher rung on its ladder of states, and after a tiny fraction of a second the electron drops back down, releasing the energy as a flash of light. This is how a neon sign glows, how a flame gives colour, how the whole lit world shines. The falling back is called spontaneous emission, and for a long time it was simply accepted as something atoms do. Excited atoms decay. That was the fact, and no one asked too hard why. But there is a real puzzle buried in that word: spontaneous. An electron sitting in a higher state is, as far as the atom is concerned, in a perfectly good state. If nothing disturbs it, the rules of quantum theory say it should stay there. A system left alone in a definite state does not change on its own. So what disturbs the electron? What reaches in and nudges it, telling it to fall, when the atom sits in the dark with nothing around it, no light shining on it, nothing to knock it loose? Left truly alone, the excited atom ought to stay excited forever. The answer is that the atom is never truly alone. Even in perfect darkness, even in a perfect vacuum with every photon removed, the electromagnetic field is still there, and it is still humming with its zero-point energy. The virtual photons of the vacuum flicker around the atom without pause, and those flickers are enough. The restless vacuum field jostles the excited electron, and that jostling is what triggers the fall. Spontaneous emission is not truly spontaneous at all. It is the vacuum, reaching in and tipping the electron off its perch. You can think of the excited electron as a ball balanced at the top of a smooth hill. On a perfectly still day, with no breeze at all, it might sit there indefinitely. But there is always a breeze in the quantum world, the ceaseless stir of the vacuum field, and that breeze eventually nudges the ball over the edge, and it rolls down, shedding its energy as light. The atom glows because empty space will not hold still around it. The light of every ordinary glowing thing is, at bottom, the vacuum-shaking energy loose from atoms that would otherwise keep it. There is a beautiful proof that this picture is right, and it comes from turning the effect off. If spontaneous emission is caused by the vacuum's field, then changing the vacuum around an atom should change how fast it decays, and you can change the vacuum. Place an excited atom inside a tiny cavity, a small box tuned so that the particular light the atom wants to emit simply does not fit, the way certain wavelengths were excluded from the Casimir gap. Rob the vacuum of the modes the atom needs, and the atom cannot fall. It stays excited far longer than it would in open space, held up by the absence of the very flickers that would have knocked it down. This has been done in the laboratory, and it works. Atoms in cavities that suppress the right modes live longer in their excited states. Atoms in cavities that enhance the right modes decay faster. By shaping the vacuum, physicists control the rate at which atoms glow. This is now a working technique with a name, cavity quantum electrodynamics, and it is a daily tool in the study of atoms and light. It is also as direct a demonstration as one could want that the vacuum is doing real work, since starving it of modes visibly changes what atoms do. The vacuum that tips atoms over also, in a grander way, decides something far deeper about the world, because one particular field never settles to zero at all, and its stubborn value is the reason anything has mass. So far, every field we have met wants to rest at zero. Remove the ripples, quiet the modes, and the field settles as low as the uncertainty principle allows, trembling faintly around a value of nothing. But there is one field in nature that does not do this. Its lowest energy state, its true vacuum, sits not at zero, but at a definite non-zero value, filling all of space evenly with a background that is simply there, in every direction, at every point, even in the emptiest reach of the cosmos. This is the Higgs field, and its refusal to be zero is why particles have mass. The Higgs field was proposed in the 1960s by several physicists working independently, among them a British physicist named Peter Higgs, whose name stuck to it. They were trying to solve a deep problem. The equations that describe the fundamental forces worked beautifully, but only if the particles carrying those forces had no mass at all. For some particles that was fine, since the photon really is massless. But other force carriers were known to be very heavy, and the mathematics rebelled at giving them mass directly. Something was needed to give particles mass without wrecking the elegant equations. The solution was to fill space with a field that does not vanish. Imagine the Higgs field spread through all of space, everywhere holding the same non-zero value, like an invisible medium filling the universe. Particles moving through this medium interact with it, and that interaction slows them, in effect, giving them the property we call mass. A particle that barely feels the field passes through easily and stays light. A particle that couples strongly to the field is gripped hard and behaves as though it is heavy. Mass, in this picture, is not built into particles from the start. It is acquired, drawn from their contact with the field that fills the vacuum. The old comparison, offered by a physicist trying to explain it to a government minister, is a crowd in a room. A famous person crossing the room draws a cluster of people around them and moves slowly as if weighed down, while an unknown person walks straight across unimpeded. The field is the crowd, the mass is the clustering, and different particles draw different crowds. Like all comparisons, it strains if you lean on it too hard, since the Higgs field is not made of people and does not cluster in patches, but it captures the essential point. Mass comes from interaction with something that fills all of space. For decades this was a hypothesis, elegant but unproven. The field itself could not be seen directly. But a field, if it is real, should have a ripple, a particle that is its own quantized wave, just as the photon is the ripple of the electromagnetic field. The ripple of the Higgs field would be a particle, the Higgs boson, and finding it would prove the field was there. The trouble was that this particle was predicted to be very heavy, far heavier than anything that could be made without an enormous machine, and so the search waited for the machine to be built. That machine was the Large Hadron Collider, a ring 17 miles around beneath the border of France and Switzerland, built to smash protons together at energies never reached before. In 2012, 2 great experiments there announced that they had found it, a new particle with the mass and the properties the Higgs boson was expected to have. The field that fills the vacuum and gives particles their mass had left its ripple in the wreckage of colliding protons, and the ripple was caught. Peter Higgs, by then in his 80s, lived to see the field he had imagined confirmed. But finding the field only deepened the real mystery, which is why the vacuum chose to hold a value at all, instead of resting at the zero every other field prefers. Why would a field settle on a non-zero value when resting at zero costs less energy and seems so much more natural? The answer is one of the most beautiful ideas in physics, and it goes by the name spontaneous symmetry breaking. It explains how a situation that is perfectly balanced and symmetric can, on its own, tip into a state that is lopsided, choosing one direction out of many when nothing in the rules preferred any direction at all. The vacuum, in settling on its value, made exactly such a choice. Picture the energy of the Higgs field as a landscape, a surface whose height tells you how much energy the field has at each possible value. For most fields, this landscape is a simple bowl, lowest at the centre, at the value 0. The field rolls to the bottom of the bowl and rests there, at 0, and that is its vacuum. But the Higgs field has a different shape of landscape, one often drawn as the bottom of a wine bottle, with a raised bump in the centre and a circular trough running around it. The value 0, at the top of the central bump, is not the lowest point. It is a hill. The lowest points form the ring of the trough, all at some non-zero value. Now the symmetry becomes clear. The central bump is perfectly round. Every direction around the circle is exactly the same, and no point in the trough is any lower than any other. The rules do not favour one spot over another, but the field cannot sit balanced on top of the central bump, because that is a peak, and the smallest disturbance sends it rolling down. So it rolls, and it comes to rest somewhere in the trough, at some particular point on the ring. The moment it settles, it has picked a direction, even though every direction was equal. The symmetry of the round landscape is broken, not by the rules, but by the field's need to rest somewhere. This is the deep sense in which the choice is spontaneous. Nothing pushed the field toward one point rather than another. The situation was perfectly symmetric right up until the field settled, and then, of necessity, it landed somewhere and the balance was lost. A pencil balanced perfectly on its tip is the same story. Every direction it could fall is equal. The setup is fully symmetric, but it cannot stay balanced, and when it falls, it must fall one way, breaking the symmetry it started with. The vacuum of our universe is a fallen pencil, resting in one particular direction of the Higgs landscape. This settling is thought to have happened in the first tiny fraction of a second after the universe began, when everything was unimaginably hot. At those temperatures, the Higgs field had enough energy to sit up on the central bump balanced and symmetric, its value averaging to 0. As the universe expanded and cooled, that perch became unstable, and the field rolled down into the trough, choosing its value, filling space with the non-zero background we live in today. In that moment, particles that had been massless gained their mass, and the forces that had been unified went their separate ways. The cooling vacuum froze into the state that shapes everything. So the mass of the world traces back to a choice made by empty space in its first instant, a symmetry broken as the universe cooled, a field rolling off a peak and coming to rest in a valley. The vacuum is not neutral. It carries a value, and that value gives weight to matter. Yet even the Higgs field, for all its importance, accounts for only a sliver of the mass you carry. The overwhelming bulk of ordinary mass comes from a different vacuum entirely, the roiling empty space of the strong force, where the emptiness itself weighs almost everything you are. Here is a fact that surprises even people who know the Higgs story well. The Higgs field gives mass to the fundamental particles, to the electron and the quarks, but the mass it gives the quarks is tiny. If you add up the Higgs-given masses of the 3 quarks inside a proton, you get only about 1% of the proton's actual mass. The other 99% comes from somewhere else. Nearly all the mass of every proton and neutron, and therefore nearly all the mass of your body, of the Earth, of the stars, does not come from the Higgs field at all. It comes from the vacuum of the strong force. The strong force is what binds quarks together inside protons and neutrons, and it is carried by particles called gluons. It is described by a theory called quantum chromodynamics, the strong force cousin of quantum electrodynamics, and its vacuum is a far wilder place than the electromagnetic one. The electromagnetic vacuum flickers with virtual photons, but photons do not interact with each other, so the flickering stays relatively gentle. Gluons, by contrast, pull on each other as well as on quarks, and this self-interaction makes the strong force vacuum churn with a violence the electromagnetic vacuum never reaches. In this roiling strong vacuum, the virtual quarks and gluons do not merely flicker at random. They arrange themselves into a persistent background, a non-zero average presence filling all of space, much as the Higgs field does but through a different mechanism. Physicists call these standing arrangements condensates, a quark condensate and a gluon condensate, and they are features of the true vacuum of the strong force. Empty space, on the scale where the strong force rules, is not empty even of structure. It is a dense, humming medium of virtual colour charge, always present, never still. When you place 3 quarks into this medium to make a proton, the quarks are not free. They're bound by the strong force, and the energy of that binding, the energy stored in the churning field of gluons that ties them together, is enormous. And here Einstein's most famous insight enters, the equivalence of energy and mass, the rule that energy has weight. The binding energy of the strong force, locked inside the proton, shows up as mass. The proton is heavy not mainly because of what its quarks weigh, but because of the energy of the vacuum-like field that confines them. Mass, for almost everything you can touch, is trapped energy. Sit with the strangeness of this. When you step on a scale, the number you read is very nearly all binding energy, the energy of the strong force churning inside your protons and neutrons, given weight by the equivalence of energy and mass. Only a whisper of it comes from the Higgs field directly. The rest is, in a real sense, the weight of the vacuum's own restless activity, made solid inside every particle of ordinary matter. You're almost entirely made of trapped energy, and that energy lives in the seething emptiness of the strong force. This is one of the deepest and least advertised truths in all of physics. The old question, where does mass come from, has a 2-part answer, and the smaller part is the famous one. The Higgs field, celebrated and Nobel-crowned, sets the masses of the elementary particles. But the mass of the everyday world, the heft of stone and water and flesh, is overwhelmingly the energy of the strong force vacuum bottled up inside the proton. Empty space is not weightless. It does the work of weighing nearly everything. And if the vacuum can hold this much energy quietly, one wonders how much force it would take to tear it, to rip real particles straight out of the emptiness by sheer strength. We have seen the vacuum produce real particles once already, when a shaken mirror pulled photons from the dark in the dynamical Casimir effect. But photons are massless, cheap for the vacuum to make. A harder question is whether you can tear massive particles straight out of empty space, forcing an electron and a positron into real existence not by shaking a boundary, but by sheer brute strength of a field. The answer is yes, in principle, and the strength required is set by a threshold called the Schwinger limit, named for Julian Schwinger, one of the builders of quantum electrodynamics. The idea starts with the virtual pairs already flickering in the vacuum. An electron and a positron wink into being and vanish, born neutral as a pair, opposite in charge. Now imagine switching on a powerful electric field across that patch of vacuum. An electric field pushes positive and negative charges in opposite directions. So when a virtual electron and positron flicker into being, the field grabs them and tries to pull them apart, the electron one way, the positron the other. If the field is weak, it cannot pull them apart fast enough before they annihilate, and nothing lasting happens. The pair flickers and dies as always, but if the field is strong enough, it can drag the pair apart far enough, fast enough, that they can no longer find each other to annihilate. The field pours in enough energy to pay off the debt, to supply the full mass energy of a real electron and a real positron. The pair, once virtual, becomes real. It has been torn from the vacuum by the field, 2 real particles now flying apart, made from empty space and the energy of the field that ripped them out. Empty space, pulled hard enough, comes apart into matter. The Schwinger limit is the field strength at which this becomes likely, and it is staggeringly large. The electric field required is far stronger than anything in ordinary experience, stronger than the field at the surface of an atom, so strong that reaching it in a laboratory has never been done. To feel how extreme it is, consider that the field needed would be roughly 1,000,000 billion times stronger than the field that holds an electron to a proton in a hydrogen atom. Fields that intense do not occur on Earth in any steady way. The vacuum is remarkably tough. It does not tear easily, yet nature may reach the Schwinger limit in places we cannot visit. Certain dead stars, called magnetars, are neutron stars wrapped in the most powerful magnetic fields known in the universe, and near their surfaces the fields may approach the scale where the vacuum's toughness begins to give. In such extreme places, the empty space around the star may not behave like empty space at all. It may bend light in strange ways and flicker toward producing real pairs, the vacuum strained near its breaking point by the ferocity of the star's field. The emptiness there is under a stress nothing on Earth can match. Physicists are also chasing the Schwinger limit with the most powerful lasers ever built, hoping to focus light so intensely that, for a flicker of a moment in a tiny volume, the field crosses the threshold and the vacuum sparks into pairs. It has not been achieved yet, but the goal is real, and the machines edge closer. To make matter from a strong enough field would be to watch the vacuum break, to see empty space converted into substance before your eyes. The vacuum can be torn, given enough force, and there is one place in the cosmos where it tears all on its own, without any laser or magnetar, simply because of the shape of space itself. That place is the edge of a black hole. A black hole is a region where gravity has grown so strong that nothing can escape, not even light, and its edge is a one-way surface called the event horizon. Cross it, and there is no coming back. For a long time, black holes were thought to be perfectly black, swallowing everything and giving out nothing, growing only, never shrinking. Then, in 1974, a young British physicist named Stephen Hawking discovered that this is not quite true. Black holes glow, very faintly, and the glow comes from the vacuum at the horizon. In time, this leak would carry the hole's entire mass away. Hawking's insight brought together the restless vacuum and the sharp edge of the horizon. Recall the virtual pairs, an electron and a positron, a particle and its antiparticle, flickering into being everywhere in empty space and annihilating before the books come due. Normally the pair is born and dies in the same tiny patch, and nothing lasting comes of it. But imagine such a pair flickering into being right at the event horizon of a black hole, in the empty space at its very edge. Now the two partners can be separated by the horizon itself, one falling in, the other staying out. If one member of the pair slips across the horizon while the other remains outside, they can no longer find each other to annihilate. The partner outside is stranded, unable to repay its debt to the vacuum by vanishing. So it escapes, flying away from the black hole as a real particle carrying real energy. To a distant observer, the black hole appears to be glowing, giving off a faint stream of particles from just outside its edge. This is Hawking radiation, and it means a black hole is not perfectly black. It shines dimly, with the light drawn from the vacuum at its horizon. The energy has to come from somewhere, and it comes from the black hole itself. The particle that fell in carries in effect negative energy inward, subtracting from the hole's mass, while its partner carries positive energy away. Each time this happens, the black hole loses a tiny bit of mass. The vacuum, split by the horizon, drains the hole. Over time, a black hole left alone will slowly evaporate, radiating its mass away particle by particle, shrinking and eventually, after an almost unimaginable span, disappearing entirely in a final flash. The vacuum that surrounds it is quietly eating it. For an ordinary black hole the size of a collapsed star or larger, this glow is impossibly faint, far colder than the coldest depths of space, and the evaporation would take vastly longer than the present age of the universe. No one has ever detected Hawking radiation from a real black hole, and it may be forever too faint to catch directly. But the theory behind it is built on solid ground, on the same vacuum physics confirmed to 12 decimal places in the electron's magnetism, and few physicists doubt that it is real. The vacuum at a horizon must leak. Hawking radiation matters far beyond black holes because it ties the restless vacuum to the deepest laws of nature, to gravity, and to the flow of heat and information in ways still not fully understood. It suggests that empty space, gravity, and the fate of information are woven together at a level we have only begun to see. The vacuum is not just a stage on which particles act. Near a horizon, it becomes a source, leaking energy no one repays, driven by nothing but the shape of space and the ever-present flicker of virtual pairs. And astonishingly, you do not even need a black hole to make the vacuum give off warmth. You only need to move through it fast enough, faster and faster, without cease. Here is one of the strangest results in all of physics, so strange it took the field a while to believe it. Two observers can look at the very same empty space and disagree about whether it is empty. To one, sitting still, the vacuum is cold and dark and utterly quiet, holding no particles at all. To another, accelerating through that same vacuum, the identical region glows with a faint warmth, a real bath of particles that the first observer simply does not see. What counts as empty depends on how you are moving. This is the Unruh effect, named for the physicist William Unruh, who worked it out in the 1970s. The connection to Hawking radiation is close, and it is no accident, because the two ideas were understood together. At a black hole, the horizon separates the vacuum and lets particles leak out. For an accelerating observer, something similar happens. Acceleration creates a kind of horizon of its own, a boundary in space beyond which signals can never catch up to you as long as you keep speeding up. That horizon does to the vacuum what a black hole's horizon does. It splits the virtual pairs, and the accelerating observer, cut off from part of the vacuum behind their horizon, sees the leftover half as a glow of real, warm particles. So the accelerating observer feels heat coming from empty space. The vacuum, which is stone cold to anyone moving steadily, appears to have a temperature, and that temperature depends on how hard you're accelerating. Push harder, accelerate more fiercely, and the vacuum feels hotter. Ease off, and the warmth fades toward the cold that a still observer always sees. The emptiness has become a thing whose very temperature is relative, warm to the one who accelerates and frigid to the one who coasts, both of them right about the same patch of space. The catch, and the reason no one has measured it, is that the effect is fantastically small for any acceleration a human being could produce or endure. To warm the vacuum by even the tiniest measurable amount, you would need to accelerate at a rate so violent that it dwarfs anything in ordinary experience, a rate that would crush any object we could build. The warmth the Unruh effect predicts for gentle accelerations is so faint that it lies far below anything our instruments can detect. It is real in the mathematics, woven into the same quantum field theory that succeeds everywhere else, but it hides below the threshold of any direct test we have managed. Physicists have proposed clever ways to see it indirectly, by watching how accelerated electrons behave in powerful fields, or by building analog systems that mimic the same mathematics with sound waves or light in a laboratory. Some of these analog experiments have seen effects that mirror the Unruh prediction closely, lending confidence that the underlying idea is sound. But a clean, direct detection of the Unruh warmth remains out of reach, one of those firm predictions of vacuum physics that we believe on the strength of the theory rather than a measurement. It sits, honestly, in the column of things the mathematics insists on, but the laboratory has not yet confirmed. What the Unruh effect drives home is how deeply the vacuum depends on the observer. The number of particles in a region, the very fact of whether space is empty or full, is not absolute. It shifts with your motion, the way the ether wind was supposed to shift and never did, except that this time the effect is woven into the accepted theory. Emptiness is not a fixed and final thing. It is a relationship between the field and the one who looks. And this restless, observer-dependent, energy-carrying vacuum raises a question that reaches to the largest scale there is. If empty space holds energy, and energy has weight, then the vacuum should have weight too, and its weight should shape the entire universe. Everything we have seen points to one conclusion. The vacuum carries energy. It hums with zero-point energy, boils with virtual pairs, holds the non-zero value of the Higgs field, and churns with the condensates of the strong force. And Einstein taught us that energy and mass are the same thing, that energy has weight and bends space through gravity. So the vacuum's energy should gravitate. It should pull on the universe, or push on it, and its effect should be spread perfectly evenly through all of space, since empty space is the same everywhere. This is where the story of the vacuum meets the story of the whole cosmos. Einstein himself stumbled onto this connection long before anyone spoke of zero-point energy, and by a different road. In 1917, applying his new theory of gravity to the entire universe, he found that his equations would not let the cosmos sit still. Gravity pulls everything together, so a universe full of matter should collapse. To hold it steady, Einstein added a term to his equations, a constant he called the cosmological constant, representing a kind of energy spread evenly through empty space, pushing outward to balance the inward pull of gravity. He put energy into the vacuum by hand to keep the universe from falling in on itself. When it was later discovered that the universe is not static at all but expanding, Einstein dropped the cosmological constant, reportedly calling it his greatest blunder. If the universe was expanding, there was no need for a fudge to hold it still, and the extra term seemed an embarrassing mistake. For decades, the cosmological constant sat in the equations as a curiosity, usually set to zero, a dusty relic of an idea that had not been needed. Most physicists assumed the energy of empty space, whatever it was, simply added up to nothing on the cosmic scale. But the cosmological constant is exactly what vacuum energy would look like to gravity. A constant energy filling all of space, the same at every point, unchanging over time, is precisely the mathematical form that zero-point energy and the other vacuum energies would take when fed into Einstein's equations. So the question sharpened into something concrete and testable. Does empty space have a non-zero energy that gravitates on the larger scale? If it does, it would act just like Einstein's constant, and it would show up in how the universe expands, either slowing the expansion down or speeding it up, depending on its sign. If the vacuum energy is positive in the way that pushes outward, it would work against gravity across the whole cosmos, driving space to expand faster and faster over time. Matter pulls the universe together, but a positive vacuum energy would push it apart, and unlike matter, which thins out as space expands, the vacuum energy would stay the same in every cubic inch, because it belongs to empty space itself. As the universe grew, there would simply be more empty space, and so more of this pushing energy, and its influence would grow until it dominated everything. The expansion would not just continue, it would accelerate. For most of the 20th century, this was an abstract possibility, a term that might or might not be there. A number most people guessed was zero. There was no evidence that empty space pushed on the universe at all, and the simplest assumption was that it did not. Then, at the very end of the century, two teams of astronomers set out to measure how fast the expansion of the universe was slowing down, fully expecting gravity to be gently putting on the brakes. What they found instead overturned the picture completely and forced the energy of empty space back to the centre of cosmology, weighing on the fate of everything. In the late 1990s, two rival teams of astronomers were racing to measure the expansion of the universe by watching a special kind of exploding star. These are called Type 1a supernovae, and they are precious because they all explode with very nearly the same true brightness. If you know how bright a thing really is, and you measure how bright it looks from Earth, you can work out how far away it is, since distant things look fainter. And by catching these explosions at different distances, you look at different eras of cosmic history, because the light from the farthest ones has been travelling toward us for billions of years. The two teams, one led by Saul Perlmutter and the other by Brian Schmidt and Adam Rees, expected to measure the universe gently slowing its expansion. All the matter in the cosmos pulls inward through gravity, and that pull should act as a brake, so the expansion today should be slower than it was long ago. The plan was to measure exactly how much the brake had slowed things down. It was careful, patient work, catching faint explosions in distant galaxies and pinning down their brightness and their distance with great precision. In 1998, both teams reached the same shocking result, independently, which is what made it believable. The distant supernovae were fainter than expected, which meant they were farther away than they should have been if the expansion had been slowing. The universe was not breaking at all. It was doing the opposite. The expansion of the cosmos is speeding up, accelerating, flying apart faster and faster as time goes on. Something is pushing space to expand ever more quickly, working against all the inward pull of gravity and winning. That something behaves exactly like the vacuum energy, exactly like Einstein's cosmological constant brought back to life. It is a form of energy spread evenly through all of space, unchanging as the universe grows, pushing outward everywhere at once. It thins out for nothing, because it belongs to empty space itself. So as the universe makes more space, it makes more of this pushing energy, and the acceleration grows. Physicists gave this mysterious outward pushing energy a name that admits how little we understand it. They call it dark energy, and it is now thought to make up most of the universe. The numbers are humbling. When astronomers add up everything, they find that ordinary matter, the stuff of stars and planets and people, makes up only about 5% of the universe. Another quarter or so is dark matter, an unseen form of matter felt only through its gravity. And all the rest, roughly 70% of everything, is dark energy, the pushing energy of empty space. The largest ingredient in the entire cosmos is not matter of any kind. It is the energy of the vacuum, driving the universe apart. The discovery won Perlmutter, Schmidt and Rees the Nobel Prize in 2011. So the restless vacuum, first glimpsed in the hum of a single oscillator and the flicker of a virtual pair, turns out to steer the fate of the entire universe. Empty space is not a passive void through which galaxies drift. It carries an energy that pushes outward on the larger scale, and that push now shapes where everything is headed, toward an ever faster expansion, a cosmos flying apart under the pressure of its own emptiness. This should have been a moment of complete triumph, the vacuum energy measured at last on the grandest stage. Instead, it opened onto this single deepest embarrassment in all of physics, a mismatch so vast it is almost hard to say out loud. Now we come to the trouble promised long ago, when we first added up the 0-point energy of every mode and watched the sum race toward infinity. That runaway sum was tamed for most purposes by clever accounting, folded into measured quantities and set aside. But when it comes to gravity, to the actual weight of empty space steering the universe, the accounting cannot hide. Gravity responds to all energy, and so the vacuum energy that gravitates should be something we can estimate from theory and compare with what the accelerating universe reveals. When physicists do this, they get the worst prediction in the history of science. The reasoning is direct. Quantum field theory says every mode of every field carries its half quantum of 0-point energy. Add these up across all the modes, all the frequencies, up to the highest energies where our current physics is still trusted, and you get a prediction for how much energy should fill each cubic inch of empty space. Feed that energy into Einstein's equations, and it tells you how strongly the vacuum should push the universe apart. The calculation is rough, but it gives a number, and that number can be set beside the measured dark energy that drives the real cosmic acceleration. The two do not match. They miss by a factor so enormous that ordinary language has no word for it. The predicted vacuum energy is larger than the measured value by something like one followed by 120 zeros. That is the gap, roughly 120 orders of magnitude. To feel the size of it, a factor of 120 orders of magnitude is vastly, immeasurably larger than the ratio between the size of the whole observable universe and the size of a single atom. The theory overshoots reality by more than the universe overshoots an atom, many times over. It is not a small error. It is the largest disagreement between prediction and measurement anywhere in physics. This is called the cosmological constant problem, or more bluntly the vacuum catastrophe, and it is a genuine crisis sitting at the heart of our best theories. Two of the most successful frameworks ever built, quantum field theory and Einstein's gravity, each confirmed to extraordinary precision in their own domains, together produce a nonsense answer for the weight of empty space. Each theory works beautifully alone. Asked to speak together about the energy of the vacuum, they give a number wrong by more than 100 orders of magnitude. Something in how they fit together is badly, deeply misunderstood. No one knows the answer. Perhaps there is some principle, not yet found, that causes almost all the vacuum energy to cancel out, leaving only the tiny remainder we measure, in the way positive and negative contributions might nearly annul each other, but for a faint imbalance. Perhaps our count of the modes is wrong at the highest energies, where our theories may fail. Perhaps the vacuum energy does not gravitate the way we assume. Each idea has been explored, and none has settled the matter. The gap remains, patient and enormous, waiting. Some physicists have reached for a more unsettling kind of explanation. Perhaps the vacuum energy could take almost any value, and does take different values in different regions or different universes, and we find ourselves in one of the rare places where it is small, simply because only there could galaxies, stars, and observers form. A vacuum energy much larger would have torn everything apart before anything could assemble. In this view, we measure a tiny value not because a law demands it, but because we could not exist anywhere else. It is a controversial idea, and many find it a retreat rather than an answer, but it captures how strange the situation is, that the emptiness may sit at a knife's edge, and that the question of why it holds the value it does may cut all the way to why there is anyone here to ask. The vacuum catastrophe forces a deeper worry into the open. We have been speaking of the vacuum as the lowest energy state, the true floor, the bottom below which nothing can fall. But what if the vacuum we live in is not the true bottom? What if it only looks like the bottom, a resting place that seems stable but is not the lowest state there is, with a deeper valley hidden somewhere below? Physicists call such a false floor a false vacuum, and the unsettling truth is that we do not know for certain that our vacuum is the real one. Return to the picture of the energy landscape, the surface whose height gives the energy of a field at each value. A true vacuum is the lowest valley in that landscape, the deepest point, a state that cannot decay because there is nowhere lower to go. A false vacuum is a shallower dip, a place where the field can rest for a very long time, seemingly stable, but which is not the deepest valley. Beyond a ridge, across a barrier, lies a lower valley still, the true vacuum, and the field is merely caught for now in the higher dip, held there by the ridge between. A field trapped in a false vacuum can stay there for an immense span of time, because the barrier holds it back the way the rim of a bowl holds a ball. But quantum physics allows something classical physics forbids. A field can tunnel through a barrier it could not climb, passing to the other side without going over the top, appearing in the lower valley by the strange permission of quantum uncertainty. If our vacuum is false, then somewhere, at some time, a tiny patch of space could tunnel through to the true vacuum, dropping to the lower energy that was waiting all along, and that patch would not stay small. Once a bubble of true vacuum forms, it would be at lower energy than the false vacuum around it, and that difference in energy would drive it to grow. The bubble would expand, its walls sweeping outward at nearly the speed of light, converting the false vacuum into true vacuum as it went. Inside that bubble, the constants of nature might take different values, the masses of particles might shift, and the physics that allows atoms and chemistry and life might simply not hold. anything the wall reached would be remade under new laws. This possibility has a stark name. It is called vacuum decay. Whether this looming scenario is real depends on details we're only beginning to measure, and one of the most important is the mass of the Higgs field's ripple, the Higgs boson found at the Large Hadron Collider. When physicists take its measured mass, together with the mass of the heaviest quark, and work out the shape of the vacuum's energy landscape, the answer lands in a strange and delicate place. Our vacuum appears to be neither clearly stable nor clearly unstable, but balanced right at the edge between them in a condition physicists call metastable. It may be a false vacuum after all, but one with a barrier high enough that it could sit unchanged for a span of time far longer than the present age of the universe. There is no cause for alarm in any human sense. If vacuum decay were going to happen, the odds of it happening in any given stretch of time are so small that the universe has already survived vastly longer than any reasonable worry would allow, and a bubble born far away could never reach us in time to matter. But the mere possibility is profound. It means the ground we stand on, the emptiness that fills all of space, may not be the final resting state of the world, only a long pause partway down. The vacuum that seeded galaxies and gives weight to matter might itself be waiting patiently to fall further still, and that same fluctuating vacuum, in the first instant of time, may have been the seed from which everything we see was grown. We end where the universe began, with the vacuum at the start of everything. In the earliest moment we can sensibly speak of, the whole cosmos was unimaginably small, hot, and dense, and it has been expanding and cooling ever since. But the very first fraction of a second holds a puzzle that the restless vacuum may solve. When we look out at the universe on the larger scales, it is astonishingly uniform. Distant regions on opposite sides of the sky have almost exactly the same temperature, the same density, as though they were once in close contact, even though they are too far apart to have ever exchanged anything. How did they come to match so perfectly? The leading answer is a theory called inflation, proposed in the early 1980s by a physicist named Alan Guth, and developed by many others. Inflation says that in the first tiny sliver of a second, far less than a trillionth of a second, the universe underwent a burst of expansion so violent and so fast that a region smaller than an atom was stretched to a size larger than a grapefruit almost instantly, and everything we now see grew from that smooth, tiny patch. The uniformity of the sky is explained because it all came from one small region that had time to even out before being blown up to enormous size. The engine of this burst was, once again, a vacuum. Inflation is thought to have been driven by a field sitting temporarily in a high-energy state, a kind of false vacuum whose energy pushed space to expand at a furious, accelerating rate, much as dark energy does today, but immensely stronger. While the field held its high value, the universe inflated. When the field finally rolled down to its true lower state, the burst ended, and the energy released poured into the hot, dense soup of particles that became the ordinary universe. The vacuum in this picture is not only where the universe rests now, it is the thing that stretched the universe into being, and here the restless vacuum leaves its deepest mark of all. During inflation, the quantum fields filling space were doing what they always do, trembling with their zero-point fluctuations, quivering faintly around their values because the uncertainty principle forbids them to hold still. But inflation took those microscopic quivers and stretched them, in an instant, to enormous size, freezing the tiny random fluctuations of the vacuum into slight variations in density spread across the whole young universe. Where the vacuum had quivered a little denser, there was now slightly more matter. Where it had quivered a little thinner, slightly less. Those frozen fluctuations became the seeds of everything. In regions that were slightly denser, gravity had a little more to pull on, and over hundreds of millions of years it gathered matter together, building the first stars, then galaxies, then the great clusters and filaments of galaxies that structure the cosmos today. The pattern of galaxies across the sky, and the faint variations in the ancient light left over from the young universe match what those stretched vacuum fluctuations predict, with a precision that has become one of the strongest pieces of evidence for the whole story. We have measured the vacuum's fingerprints written across the sky. Take that in fully. The galaxies, the stars, the planets, the atoms that make you, all of it can be traced back to the tiny quantum trembling of empty space in the universe's first instant, stretched by inflation into the seeds of structure. The same restless quiver that keeps helium from freezing and tips excited atoms back down was, at the beginning of time, the pattern from which all the structure of the cosmos grew. The vacuum did not just fill the early universe, it sketched the blueprint of everything that would later form within it. And with that, we can return, at last, to the jar in your hand and answer the question we began with. Come back now to the jar you emptied at the start, the one you pumped free of air, swept clean of every atom and cooled toward the coldest cold there is. We asked a simple question then. When you empty a box completely, what is truly left inside? We can finally answer it plainly, in the light of everything the physics has shown us. What is left is not nothing. What is left is the vacuum, and the vacuum is a full and restless thing. Inside that jar, even with every particle gone, the quantum fields remain, because they are woven into space itself and cannot be pumped out. They tremble with zero-point energy, unable to hold still, humming their lowest note forever. Virtual pairs of particles flicker into being and vanish, a constant quiet boil of matter borrowed and repaid. The Higgs field holds its non-zero value throughout, giving weight to any particle that passes through, and spread evenly across it all is the faint dark energy that pushes the whole universe to expand. The emptiness in your jar is a sliver of the same active vacuum that fills the cosmos and steers its fate. We know this is real because the vacuum leaves marks we can measure. It shifts the light of hydrogen by the amount Willis Lamb found. It sets the magnetism of a single electron to 12 decimal places, the most precise agreement in all of science. It draws two plates together with the Casimir force, glows into real photons when its boundary is shaken, and tips excited atoms back down to make the ordinary world shine. Empty space is not an idea or a manner of speaking. It is a physical medium, humming and flickering, and we have felt its touch again and again in the laboratory. And yet, honesty asks us to hold the mystery alongside the knowledge. We do not know why the vacuum weighs what it does, and our best estimate of its energy misses the measured value by more than 100 orders of magnitude, the worst prediction physics has ever made. We do not know for certain that our vacuum is the true and final one, or only a long pause partway down towards something deeper. The vacuum is at once the most precisely tested thing we have, and the site of our largest unsolved puzzle. We have measured its whisper to astonishing accuracy, and still cannot say how much it weighs. What is certain is that the old picture of empty space as a pure and simple nothing is gone, and it is not coming back. The vacuum is a somewhere, not a nowhere. It hums, it flickers, it holds energy, it gives mass, it pushes galaxies apart, and in the first instant of time its tiny quiver was stretched into the seeds of every star and every galaxy, including the one you live in, the atoms of your own body traced back to the trembling of empty space. So the space just past your fingertips, the gap you could wave your hand through without feeling a thing, is not the absence you took it for. It is a quiet, restless, energy-carrying medium, the same one that fills the whole universe, the same one from which everything grew. You're not surrounded by nothing. You're surrounded by the vacuum, full to its faint humming brim, and you are made of what it became. The emptiest place you can imagine turns out to be the fullest, and it has been holding you and building you all along.